Parallel query processing. Let's start with a little history. So the relational database was invented around the 1970s, and the basic idea was to use declarative set-oriented primitives and isolate programmers from the physical hardware. In particular, allow people to have declarative queries that would say what they want, but not how to get it. And this was used in the 70s to allow for flexible disk layouts of the data. And data layouts could change on disk without the user knowing. And a query optimizer could jump in and choose a different query plan every day to run the same query that the user asked every day. And then in the 1980s, what people realized was that this declarativity and this set-oriented computation could be used not only to optimize for disks, but also to optimize for using multiple computers at once, for using parallelism. And one of the key observations in the database community at that time was it didn't require specialized hardware to do this. You could do this on regular old computers that were being sold off the shelf, connected by a high-speed network. And this was pretty countercultural at the time because a lot of computer hardware researchers wanted to build custom machines for parallelism. But the database community learned very quickly that it's more economical to use commodity hardware for those purposes. And so in the 80s, there's quite a lot of invention around parallel relational databases and scaling up, which we'll talk about. But in the 2000s, what happened in the web properties was that people wanted to scale up even further. And the name that stuck on this was big data. And so these are things like MapReduce and Spark. And really the only difference between this work and the earlier work on parallel relational databases was in the scale. As you start to look at thousands of machines and beyond, you have to begin to worry about some of the peculiarities that arise at that scale. So we'll talk about that in a future lecture. Today we're going to focus though on the fundamentals of parallelism that apply both to the traditional parallel relational databases and the larger scale problems that we're looking at today. So why parallelism? Well, this guy over here is pretty happy, and he represents the idea that parallelism is all about I/O bandwidth. It's all about how much data you can move through the pipes of your system at once. So with a single straw, or by analogy with a single disk arm on a single disk, how long would it take to scan 100 terabytes? Well, at a half a gigabyte per second, that's 200,000 seconds, or 2.31 days. It's a very long time to scan 100 terabytes. So what can we do about that? Well, it's really very simple. More straws. Running at a 100-way parallel turns it into a 2,000 second problem, which is only 33 minutes. So the basic idea is just to take a big problem and break it up into many small problems. And the only trick here is to figure out a way to make those small problems independent of each other so that they can run at their own speed and everybody can just focus on doing what they do as fast as they can. And then the collective system will finish very quickly. So when we talk about parallelism, there's actually different metrics that people talk about, and we want to shoot for both of these. The first is what's called speed up. And the idea is that if you have a fixed workload, so let's say you have a particular query over a particular database instance, so it's a particular set of data, if you throw more hardware at the problem, things should get faster. And in particular, as you throw more hardware or parallelism at it, you'd like it to get linearly faster. You'd like your throughput to go up linearly for your workload. Okay, so that's a kind of ideal linear speed up curve that we see in this picture. Scale up is a somewhat different metric that's quite common and makes sense in environments where what you're doing is you're growing your workload while you grow your hardware. So here, as you increase your workload, let's say your data grows and your parallelism grows at the same time, you want your throughput to remain the same. Add more work, add more machines, keep your performance, right? So for scale up, the ideal here is to have a flat curve where as you increase the size of the problem, the throughput remains the same. And so sometimes you want to shoot for one, sometimes you want to shoot for the other. In general, with databases and parallelism, we'll see if we can do both. And oftentimes we can do pretty well with linear speed up and scale up. Generally speaking, when we talk about parallelism, there's kind of two categories of parallelism to exploit. So if we take one of these ovals to be any sequential program, like for example a relational operator like select or join, pipeline parallelism, which is shown here on the left, is to allow multiple stages of nested functions to run at once. So you can see the bottommost blob on the left, which is blue, is f. It's the function f, and it's running on some x3. And then one level up from it is a green bubble, which is running g over the results of a previous computation. So this is g over f of the previous object, which is x2. And above that, there's a white oval, which is running function h on the results of g from the last step, which is g of f of x1. So all three of these are running in parallel on three different x's in a pipeline fashion. So that's pipeline parallelism. On the right-hand side, we've got what we call partition parallelism, where we take x and we run it a hash function on it. So each item of x goes to a different machine, and then each one of these machines runs f of x at the same time. So on the right-hand side, we're parallelizing f. On the left-hand side, we're doing pipeline parallelism. Notice that on the left-hand side, our parallelism is limited by the depth of our pipeline. We can only get parallelism 3 in this example because we only have 3 functions. On the right, we can partition this thing by as many data objects as we have in some sense. So the partitioning scales up and the parallelism scales up to the amount of data. Now you can do both of these kinds of parallelism at once, and we'll refine some of these ideas soon. But basically, these are our two coarse-grained kinds of parallelism. You can even use them together. So keep an eye out for both of these as we talk through our various parallelism schemes going forward. Now in databases, it's actually easy for us to say this because it's easier for us to do this. In some cases, getting pipeline or partition parallelism can be hard. We actually have some advantages. We have lots of data, and we have batch operations on that data, so set operations, which means, and we have our pre-existing divide and conquer algorithm. So we already know how to divide up this data and conquer it piecewise. So those pieces can be handled in parallel. That we also, in addition to that partitioning ability, we have natural pipelining in a lot of our operators. As we saw with the iterator model, we get pipelining kind of for free. And then finally, one of the key issues here is we can introduce parallelism into database systems without affecting the clients of the system in any way other than maybe they get faster. So these declarative languages allow the clients to say what they want, and we can adapt the parallelism strategy to the task at hand and the hardware we have available. All of this without changing the program. So Cont's physical data independence, which was originally conceived for handling disk drives, is very useful here for enabling parallelism.